Hello everybody, it's my absolute pleasure to introduce you to Martin Hedges from Neotech, who's now going to give us a talk on scalable 3D printed electronics. I'll turn off my camera and microphone, hand to Martin, then I'll reappear when we've got about 5 minutes to go. Over to you, Martin.
Okay, thank you very much. Welcome everybody. So I've got 15 minutes or so to talk. This is my agenda so far. So I've got one slide on the company overview. I'm going to talk a little bit about designing a 3D printed electronics process, how we put that together. I'll talk about some application examples and sort of going beyond sort of simple circuits, looking into the aspects of, say, fully additive 3D printed electronics. And then I'll have one slide at the end just to explain how print systems, how the hardware looks like. So Neotech, we're based in Nuremberg, Germany, and we're machine tool manufacturers focused only on 3D printed electronics. So we don't do anything else. We build systems for this particular purpose. We've been pioneering this work since about 2009. We built the first system in 2010. And we always had the intention of moving to volume production. So we developed and patented the 4-5X system. So that's a 4-print head system working with 5-axis range of motion that can scale the process to volume manufacture. So that was done in 2012, and we've had some commercial success on that. Installing the first system of that type in 2013. And the first mass production really in 3D printed electronics then started in 2015. So we've already come quite a long way. But before I sort of go into the technology in more detail, maybe some of you are wondering, what is the reason for doing this? Why do we need 3D printed electronics? And there are three main aspects, headings really. One is the design flexibility. You move away from 2D, you go into a 3D world, then you can obviously get flexibility of shape, more integrated products, you get miniaturization, new functionality. Then you also have to consider economics. Now, economic benefits can come from different sources, the reduced number of processes that you have in making your electronics or mechatronic systems. You can have increased reliability, so that economic aspects. And then also, like a lot of printed electronics applications, there's the environmental benefits compared to a classical PCB based electronic system. Good. So that's why you would want to look at it. So what I thought I'd do here is to show a video of a couple of print processes working. So we work with a variety of printing techniques, really depending upon the application that you have. So what you're seeing here is my favorite process. It's a jetting process. It's a very simple process. So we have in the orange syringe there a paste. In this case, it's very much like a screen printing paste, and that's jetted onto the surface. And you can see the print head being manipulated over the surface, working with those 5-axis range of motion to print in 3D space. What you will also notice as well is that we have a gap. You can see that we can actually throw the ink using these types of processes. That really enables us to work, at relatively good speeds on a 3D surface, even if we don't know truly what the 3D surface is. So there you see this screen printing paste. It's been printed in fairly thick. Those lines there are about 300 microns. Now, if you want to go finer, then you maybe have to use a different process. So this is a process called nanojet from the American company IDS. So this is an aerosol technique. So what you're doing here, you're printing much finer lines. So in this case, we're using a nanoparticle ink that is aerodynamically focused. Again, you can quite clearly see the standoff distance, but what that allows you to do is to actually get some different kind of result. So instead of having a piezo jet, we've got a viscous paste, a screen printing type material that goes down very thick. It has relatively wide feature sizes. With the nanojet type process, you go to finer lines that use more fluid inks. You have thinner layers. So there are really many different types of techniques you can use in designing your print process. Good. So, how scalable is this? I mentioned in my slide on the overview of Neotech that we've had some volume manufacturing success. So what we did initially, we were working, way back in 2012. We're printing on components that are produced by traditional manufacturing techniques. So that could be injection moldings, or it could be a composite, or it could be a forged component, or whatever. But basically what you're doing is you're printing onto an external surface. And as time has gone on, so I think about 2016, we started to actually look at a different process route, which really then is more focused currently at prototyping, maybe potentially near term through to medium volume manufacturing. And that's by combining these printing processes with classical 3D printing. So I think most people are familiar with plastics 3D printing, so use FFF, fused filament fabrication, build a mechanical structure. And then within that process, you can add your surface mount devices. So if you want to put chips, resistors, LEDs in, we can pick and place those. We print the circuits within that structure. We then print the interconnects to make the fully functioning connection to the surface mount devices. And then you go around this route of printing more mechanical structures. You maybe have some post-processing. So that's an alternative route where you can actually build up with electronics, not just on the outside, but also on the inside of a structure, which gives us some very interesting design possibilities. So I'll look at some current applications that we're working on that are being addressed based on this traditional route of printing on existing structural parts made by standard techniques. So being based here in Germany, we have a lot of work ongoing in automotive. All of these are really the development stage, no mass production yet. I think those things are going to be a couple of years out. Heater patterns, various types of heater patterns that can be printed, sort of LiDAR, radar devices, keeping those snow and ice free for autonomous driving. We can print on rear windscreens. If you're looking to save weight, you can replace glass with injection molded windows. And in that case, you actually have a 3D structure. You need to be able to put electronics onto that. Or if you move away from petrol and diesel motors to electrification, you've got to be able to heat the cabin interior. You can't use the waste heat from the engine for that. There are also lighting applications, so combining surface mount devices with printed circuits. Add some aesthetic features like optical waveguides. Yeah, I think towards the end of this year and into next year, we'll also be looking at 3D printing of OLED type materials. So taking OLED materials and putting those on 3D surfaces. Sensing can also be done. And sustainability, that's going to become more and more important over time. Weight reduction, the fact that you can reduce the number of parts, reduce the wiring bundles. Looking also, we've got a lot of work ongoing on automated recycling, looking at the sustainability aspects of making these electronic structures. We've done previously a lot of work, and still a lot of work is ongoing in cell phones. So what you actually see there on the top right-hand corner is an example of one of the 4.5X systems working in a mass production scenario. So we're printing conductive materials typically onto an injection molded material, polycarbonate, PA, those kinds of materials. What we're also doing now, we're going beyond that and applying printing very fast and then using a subtractive step. So we're using laser ablation now to actually cut and trim those structures. There are certain benefits that you can get with that, so you can make finer features, more accurate features at a much higher speed and a much lower cost than just by printing alone in that case. Good. Another application here that was recently actually sent up into the stratosphere. So this is a box, injection molded box, polycarbonate, and that has 3 antennas on that. So that just shows you the ability to also, with some of the techniques, to access the internal structures on a molding in this case to create some quite novel devices. Healthcare is another area. There's an example here from one of our customers, Everyoung Biodimension in Taiwan, who printed this rehabilitation ball, so printing on a sphere, printing the circuitry to connect up these surface mount devices, to use that as something for patients to continue their rehabilitation by squeezing, mechanically working the ball. And you can track all of the data and see the progress that the patient's making there. Aerospace is another area. We get involved really mainly in commercial aerospace applications. We don't get involved in military applications. There's an example here. This is, some of you might remember, flying on aeroplanes. This is a cabin panel lining, so it's a composite structure, honeycomb composite structure, and this is a thing that you sit next to where you have the blind on the wall there. And then putting electronics onto that lightweight structure and through that structure. Touch sensors, heater patterns are the current demonstrators for that field. Good. So those are some of the examples that I've talked about on the printing with using traditionally manufactured components. So I want to just show a couple of examples now on fully additive 3D printed electronics. So this again is a combination of 3D printing plus electronics. So this is an application was developed by the University Erlangen-Nuremberg FABS department, and they've basically 3D printed an egg timer. So they have a touch sensor on the top. They control those LEDs, and the LEDs are controlled by a timing circuit that is in the controller that you can see. If you look at the images at the bottom there, on the bottom right-hand side, you can see the controller there embedded really in the center of the egg. There's a buzzer there for an acoustic signal, so when the egg timer is finished, it will buzz, and obviously the lights will flash. And that's quite interesting, that you've got this embedded structure with the electronics. We've got something like 2 meters of circuits in there, and you've got electronics inside and outside. So the body is built by 3D printing, so free fused filament fabrication. The electronics are added, the circuits are added during the build. Yeah, so that's something that is pretty novel and pretty new, that can be done with this kind of technology. We also have a similar kind of program, similar set of work, doing the same kind of thing with ceramics. So we had a project Ampex, additive manufacture, printed electronics with ceramic substrates. So in this particular case, we're dispensing ceramic paste, in this case an analog to LTCC materials, low temperature co-fired ceramics, which is alumina-based ceramic materials that are used in high temperature circuit boards. But we're printing that, and we've shown the ability to actually embed functioning electronics within that 3D structure. And that work will now be carried on with the Additive for Industry, a German federally funded project, looking at applications, high frequency antenna and sensor circuits. So again, using, in this case, a dispensing technique to dispense a mechanical structure, and then putting electronics inside and outside. Good. So how does this look when you look at the actual the products, what we manufacture? So you have the ability then to select a print platform, so you can have multi-head print systems where multiple heads are working in parallel. For volume manufacturing, you can have a single head, and I say single head, that's like any given time only one head is active, but multiple heads can be in there, different tools. And that's really focused at R&D and product development. We build those systems in various sizes. Integral to that offering is also then the CAD-KAM software. You have to be able to program all of these machine tool operations, the printing steps, the pick and place, the slicing for the additive manufacturing. So you have to be able to do that. So we have our own proprietary CAD-KAM system for that has all of those tools embedded within it in a single interface. So you're combining the electronics with the mechanics in your CAD-KAM process. And then what you can do is you can select then the printing tools that are most appropriate. So I've showed the video of the jetting, we've seen aerosol-based techniques, we have single nozzle and also classical multi-nozzle inkjet. I've mentioned the fact that we also use dispensing, mainly for building mechanical structures, but not exclusively. We have FFF process. We have pellet extruders if you wish to work from pellets. If you wish, you also use, we've done some work also dispensing MIM materials, metal injection molding, and then pick and place. So those are the things that actually add your electronics functionality or your mechanical functionality or potentially your optical structure. And then you have pre and post processing tools that you can also include within that process chain. So you might want to clean up a surface. You have a machining head to clean that surface. Plasma cleaning, you might need to increase the surface energy of your structure that you're printing onto to make get better adhesion, get better wetting of your inks and pastes. And of course, if you're working, all of the electronic materials coming in liquid forms, so they're a paste or an ink, they have to be dried, they have to be cured, they have to be sintered. So then you would do the standard. There's no real magic in that. You can use light, you can use lasers for sintering. If you've got a UV curable material as a dielectric, for example, you have to use UV light. So you have all of those tools that you then combine with your print and functionalizing tools to help you complete the process to get the required properties. Good. So we talked a little bit about scalability. One of the things that we have to consider, if you think about the example of the egg that we built, is that you're actually embedding structures potentially. And obviously the build times can also be quite long if you're working with building a mechanical structure through classical 3D printing. So obviously you need to be able to control the quality if you have structures, electronics inside the mechanical body. That's even more important than if you're printing on an external surface. So there's currently a project ongoing looking at automated quality assurance. So this project is called QA-KAM. It's funded by the German Ministry for Business and Energy. And the idea is that we have a vision-based system that will actually automatically record the printed structures in your 3D printed device. So these are things that, as it's been built layer by layer, will record that data. It will compile those images. It will compensate for any distortions from the camera. So we should be able to get width and height and get different views on the printed structures. And then it will use artificial intelligence to check for potential defects. So have we got a break in the line? Have we got a short circuit? Are there some other defects? And then depending upon the defect type, it will do one of three things. It will either automatically correct, which might be quite simple. If there is a case of a break in the line, it knows the position, it can go back and print that again. But other things might require some operator input, or it could be that we actually have the situation that the system just decides it will abort that print, and carry on to the next one. So that for me is very, very exciting development. To put some intelligence, into this process chain to help us scale, to get the reliable part into the electronics. As I say, that's especially important if you're mixing multiple materials. You're embedding structures. Good. So with that, I'm probably a little bit ahead of time, but that's good. We can have some more questions. So the summary, designing the 3D printed electronics process. We've talked a little bit about that, using the different types of printing techniques, and I've showed some current application examples. Some of them are quite relatively simple, antenna or a heater pattern or something, but you can also have the ability to have more complex electronics devices by combining surface mount devices. And then finally, we took a very short look at this concept of fully additive 3D printed electronics. So that combination of classical 3D printed plus electronics. And with that, I would like to thank you for your attention.
Thank you, Martin. That was a really interesting talk. Thank you very much for that. Audience, do please leave any questions that you might have for Michael. You can post them on the chat board. Kasha, actually, from TechBlick has left you a question, Martin. How do you make vias between the different layers in a 3D structure?
In short, we actually don't. So if you think about a classical 3D printing process, XYZ, you're stacking 2D layers, and then you would have, like on a PCB, you would have to create a via and then connect into that. That has the issue that you're basically writing a vertical wire, and it can be done. But it's not the most efficient way to work. So what we generally do is we build up the next layers, and we obviously leave a gap, but we will actually build a ramp that we can access. And then we basically print down the ramp. So rather than every single layer, I have to swap my tools over. So I'm printing with the FFF, and then I get to the end of that layer, and I have to then come in and fill a hole, and then go back again, FFF. What I'll do is I'll build my mechanical structure much further, and then actually have a ramp that I can just print down and contact to the layer below. So there's certain things you can do by using that 5-axis range of motion. So that means that you also work in a more efficient way in terms of cycle times. You're not constantly swapping the tools. Also on the materials, because if you build a via, you've maybe got 0.5 millimeter diameter, for example, and that's going to be 0.5 millimeter diameter vertical wire, when you only need 300 microns wide by 20 microns thick up a ramp. So Yeah, we generally work with ramps using the 5-axis motion.
Great. Okay. Any more questions? I can't see any more coming in. Michael, just a quick question from me. How do you think the printing of mechatronic systems will change manufacturing? And, what possibilities will that open up?
I think for me, again, there are these two process chains that we have. So printing on existing structures. So I think I would like to see as we get better and faster. So again, costs. We can't deny that cost is always going to be an important factor. So printing on existing structures will get better and faster at that. I think, but the really exciting thing is this combination of 3D printing plus the electronics plus optical, so 4D printing effectively. So I think that is something where you can get some really, really novel devices. I think we have to obviously work on the scalability, making those processes, making the machine tools and processing lines, designing processing lines that can work effectively and work in a fast way, again, with the reliability. So I think those things are very important. But we also have to be very careful here because, of course, if you think back to the egg situation, very, very good design. But if you start embedding things right in the center of a structure, that makes recycling a lot more difficult.
Yeah.
How am I going to get to that chip? So I think design, as we learn about the technologies, we need to take care to make sure that it is a sustainable thing and to really use the benefits of printed electronics in a good way.
Brilliant. Well, thank you once again for a really informative talk. Martin will be available. We just had another question come in from Daniel Brown. How big do you think the market is for this equipment?
At the moment, obviously, I have a very good overview because we're making and selling systems effectively and have been doing for a number of years. I think it's still quite niche. But if you look at the potential, and then you look at some of the applications in cell phones, you can very quickly, if you happen to catch the wave and catch the application as it takes off, the scalability there, or the number of systems that you need is potentially very, very large. I think the other interesting application idea is that also this is very transferable across industries. So if we print antenna for automotive, it's based on work we've done on antenna in cell phones. So it's really scalable across many, many industries. So at the moment, it's niche. Obviously, I hope that's why we're doing it, that it will be large.